Okay, speaking of the test tomorrow, if you haven't looked at your email, you need to let me know how you want to take the test. So option number one, you come in here, you take the test in here. If you want to, that's fine. Feel absolutely no obligation to come up here and take the test up here. Some kids said they wanted to just because they're back in the environment of the school. So if you want to come up here, I'll keep you isolated. You can take the test up here. Second option is that I send you the test and you print it out. I'll send it as a PDF file. I'll send it out tomorrow morning. You print it out. I need it back by 4 o'clock tomorrow afternoon. Third option is if you don't have a printer, let me know. I'll print one out. I'll have it up in the front office. You come up to the school, you pick it up from the secretaries. I still have to have it back by 4 o'clock. So listen to me. Usually I am forgiving on late work, okay? I take I'll give you some grace. This one, I will not. So if you're going to take that test at home, print it out, or if you come up to the school and get it, so help me, unless you have a leg completely severed, not cut off, not just dangling or broken, unless your leg is completely severed or something of that equivalence, you have to get that test to me by 4 o'clock or I'm not even going to grade it. So I want everybody to be perfectly clear on this, and I'm recording it as God is my witness. I'm going to tell you right now, if I do not have that test back by 4 o'clock, 4:01, 4:15, doesn't matter. 4 o'clock, I'm shutting it down. So if you're going to take it at home, you have the respect of me and my deadline to get it back to me by 4 o'clock, or so help me, it's just going to be 0 in your grade book. Okay? I'm letting you take it at home, but you have to work with me on this. So I want everybody to be perfectly clear. You have until a deadline at 4 o'clock to get me that test if you're taking it at home. So if you want to make sure that you get this done in time, make sure you get it before that deadline. Okay. Now, let's talk about, speaking of Lunar Command Module, so let's talk about number 5. So on number 5, here's what you're going to do. You want to figure out how fast this thing is going. So when in doubt, kind of make a sketch. Say, okay, here's the moon, and I tell you that this Lunar Command Module is 72 kilometers above the surface, and then you have the radius of the moon is 1738 kilometers. So here's what you got to do. You got to take the 1738, add that to the 72, that becomes your orbital radius, change that into meters, and then it's just a plug and chug type affair. So your answer to number 5 should be something times 10 to the third meters per second. Okay? You should start with a 1 and then be times 10 to the third meters per second. Your answer to, I'm just going to give you some range of answers. Okay? So your answer to number 1 should be something times 10 to the third kilograms. And the whole key to number 1 is the word identical. So on number 1, I want to make sure everybody starts this one right. So you're going to start with F equals big G, M1, M2 over distance squared. Okay? So because these are identical, you could let M1 be X and then let M2 be X. Now, here's where this goes south. You look at this and go, oh, X and X, oh, that becomes 2X. Okay? We're not adding X and X. We're multiplying this together. So this becomes X squared. Okay? Don't look at this and go, oh, that's 2X. No, it's X squared. Okay? Now, if I had said one mass is twice the other one, then let's say on the test I changed it up a little bit. And I go, okay, hey, one mass is twice the other one. Then you would have X and 2X, and then it would become 2X squared. Okay? But as long as they're just identical, it's just X times X or 2X or 3X or whatever it's going to be. Okay? So that answer is going to be 10 to the third. On number 2, what center to center distance of the Earth would a 1 kilogram mass weigh 3 newtons? So basically what I'm saying is here's the Earth. Okay? You have a 1 kilogram mass, and I want it to weigh 3 newtons. So here's the $1 million question. Fg equals mg. Okay, so basically, what does G have to be to produce a gravitation for something to weigh 3 newtons? Lauren, what is little g, which would be my rap name I've determined, okay? If I become a rap star, that would be my name, is little g. So, what's the value, Lauren, of little g if this thing is going to weigh 3 newtons? You do not make this difficult. You're making this difficult, Lauren. No? No, because here's the reason why. If g was 9.8 meters per second squared, and I multiplied that by 1 kilogram, what would it weigh?
Oh, wait, it's 3.
It's just 3! Yes! That's why I said don't make this difficult, and you made it difficult. I told you, don't make it difficult. Don't make me put that pirate hat back on. I will, okay?
I think I should put my hat. Actually,
You want the pirate hat back on?
I think everyone would probably agree with me.
Okay, all right. I'll put the pirate hat back on. Okay, but I'm not doing anything weird. Like, yeah, I'll go with the pirate hat. Better? Okay. Alrighty. Okay, so we might have to have like different themes. So now we have the pirate day. Okay, so here's the deal. So we got 3 newtons is going to equal 1 kilogram times x, so that's going to be 3 meters per second squared. So basically what we're trying to figure out is that if you're here on the Earth, I want to know how far do I have to go so that when I drop this 1 kilogram mass, it begins to accelerate at 3 meters per second squared. So obviously I've got to be out here quite a ways, because if I'm just at the surface of the Earth, it's just going to be 9.8 meters per second squared. So I've got to be out here quite a ways so that when I drop it, I get that acceleration to 3 meters per second squared. So since I'm wearing the pirate hat, we're going to solve for R, right? So R. So we've got, this is like a pirate doing a rap song, okay? So we got little g rocking out the R, ready. So I got little g equals big GM over R squared. So I want to get R by itself. So I have big GM over G. Now, listen to me, listen to me, listen to me. Do not put in 1 kilogram for this mass. This is not 1 kilogram. This is the mass of the Earth, okay? It's what is falling towards the Earth, not what is it's what you're falling towards, not what is falling. So don't put in 1 kilogram here. You have to put in the mass of the Earth. So if you do that right, you're going to get 10 to the 7th. Okay? Cool with that one. What?
Amanda needs let back in.
Oh, seriously? No, I don't think we should. Okay, I'll let her back in. Amanda, we didn't mean to kick you off the pirate ship. We let you back on, okay? So,
So, when I was like first logging on, my computer was updating, and I had to log in on my phone.
okay, I know that feeling. Okay, all right. So you logged back in and I'm back wearing the pirate hat, so that kind of flipped you out, I'm guessing. Okay, now let's talk about problem number 7 with the Lagrange points, okay? So here's the Earth, here's the moon, okay? And we went through all of that math yesterday. So basically, one Lagrange point is going to put you here. The second Lagrange point is going to put you out here. So your first Lagrange point should start with a 3 and be something times 10 to the 8th. Your second Lagrange point should start with a 4 and also be e to the 8th. Okay? Now, don't everybody gets so happy when they find the Lagrange points that they forget to answer that other question. And I say, once the limb crosses L1 as it approaches the moon, what will happen to its velocity? Explain. So, when the Lunar Command Module crosses this point, what's going to happen to its velocity? So there's a couple of different ways you could view it. One option is that you could view it as like a curvature of space and time. So that L1 is like the top of the hill. So once you cross over that point, you're going to be in the gravitational well of the moon, and you're going to start to speed up. Okay? So if you're a subscriber to Einstein, that's the approach that you would take. Oh, we're going on the downhill curvature of the moon. It's like a sled, and you're going to start to speed up. The other option is that you can look at it in terms of net force. So once you cross L1, and I want you to get this out of your mind right now. Don't think that when you cross L1, you're no longer in the gravitational field of the Earth. You still are, okay? When you're orbiting the moon, you're still in the gravitational field of the Earth. So, but what happens is a net force situation. So if here's the Earth and here's the moon, okay? Then if you look at this as this thing goes, you're going to start off with some net force being pulled back towards the Earth and less towards the moon. As you get further and further and further towards the moon, that gravitational field is going to get stronger to the moon, and it's going to get weaker towards the Earth. So imagine as you go, this arrow is going to get bigger, this arrow is going to get smaller. Once you cross that Lagrange point, those two arrows are exactly the same. Then once you cross that Lagrange point, then the bigger arrow is going to point towards the moon, and the smaller arrow is going to point back towards the Earth. So don't tell me, oh, once you cross this L1, you're out of the gravitational pull of the Earth. You're not. You're still in it. But this becomes your dominant force is towards the moon. So let me give you some perspective of trying to hit and launch something to the moon. So this is why I had this apple. So trying to get a spaceship from the Earth, orbiting this, and going towards the moon. So here's the analogy. So imagine that I take this apple and I put it at one end of the football field. Okay? So I've got this apple sitting at one end of a football field. I'm going to be at the other end of the football field, standing at the other end zone 100 yards away, and I'm going to have a .22 rifle. So I'm 100 yards away, and I'm going to have this apple. So the apple is like the moon. So the analogy is that I've got it, when I'm going to try and hit this apple 100 yards away. But not only I don't want to hit the apple, okay, because that's going to be bad. All I want to do is nick the surface of that apple. Okay? All I want to do is just nick that surface because I want to get caught in that gravitational field. So if you've ever done any kind of like long distance shooting with a gun, imagine being 100 yards away and you're trying to nick the edge of this apple. That was basically the challenge that the engineers faced trying to get the Lunar Command Module to orbit the moon. It was that far away and it was that technically difficult. Okay. On number 9, now let me point out one thing about what I want on number 9. Okay? So on number 9, I want to know how high above the surface of the Earth must the GPS satellite be? Okay, so what you're going to do on number 9, you're going to go back to the pirate's favorite equation. Okay? And I've given you the period. Okay? You know that. That's 24 hours. Make sure you change that into seconds. You know the mass of the Earth. You're going to solve for the radius. Okay? Now, when you get that initial radius on number 9, that initial radius is going to be from the center of the Earth out to that satellite. Okay? That's where this is going to be. But what I want is how high above the surface of the Earth this is going to be. So when you get that answer to number 9, subtract out the radius of the Earth, because I want to know how high above that thing is going to be. So your answer to number 9 in that exponent should be something times 10 to the 7th. Okay? So on number 9, that final answer should be something times 10 to the 7th. So the cool thing, and it's funny, if you look at physics books, even like when I was in college in like the late 80s, you couldn't find any mention of geosynchronous satellites because we didn't need them. So it wasn't until about 10 years ago that it actually started with the military, and the reason that we have to have geosynchronous satellites is because that allows us to have fixed points in space. So on a geosynchronous satellite, like you would park a satellite right above, say, Mays, Kansas. So as Mays is spinning on its axis, that satellite is staying above that same point. So how your GPS system works is called a triangulation of data. So you cannot determine your location just upon one satellite. You have to bounce it off of a minimum of 2, preferably 3. So what's happening, your phone, if you're using, Google Maps or whatever, your phone is continuously bouncing signals off of these satellites and is keeping track of where you are based upon these fixed points. So if the satellites were in near Earth orbit, they would be going faster, and you couldn't use them as fixed points. So that's the importance of having these geosynchronous satellites. So basically, we have a parking lot around the Earth of these geosynchronous satellites, and that's what allows us to navigate. On number 9, when you're going to figure out how long it takes for that signal to travel, on number 9C, that answer should be less than 1. Okay? That's the only reason it works. Because if that satellite signal took a long time to get from that satellite to your phone, if it was like 3 minutes, well, you'd always be having this time delay and it wouldn't work. So thankfully it's traveling at the speed of light, so your answer to 9C should be less than a second. Now let's talk about 13, because you guys are going to actually end up doing a lot of calculations involving electrical forces. So on a 13, I just kind of give you this so you can kind of see the relative amount of force of the electrostatic versus gravity. Because again, physicists were initially very excited based upon the work of Ernest Rutherford, because he said, oh, the nucleus is really small and dense, and the electrons, based upon the Bohr model, are moving around. And they said, oh, these are all physicists. They said, we can do these calculations. This is simple. We're just going to model it as like a small solar system. Instead of the sun, we're going to have the nucleus. Instead of planets, we're going to have electrons. And they thought, they were literally going, this is cool. But here's the problem. Electrons, when they move in circles, they're accelerating because they're moving in circles. Remember that for the test, by the way. You cannot travel in a circle without accelerating. You can travel in a circle at a constant speed, but you cannot travel in a circle without accelerating. So what happens is that what should happen is that the electron loses its energy and the electron would collapse into the nucleus. So it would be like me spinning this rubber stopper around over my head, and then eventually I get tired and I lose energy, and then it collapses down into the lowest energy state. So eventually what you'll see is that we had to explain why the electrons don't do that, and why this table is still a table, but yet I can look like I have a pirate. Oh, that's kind of weird. Wow, look. I can move my hand through my hat. Okay. Hours of entertainment fun right there. Okay, I know you all wish you could have a pirate hat too. Okay, so your answer, because it all kind of builds off of each other, your answer to 13A should be 10 to the negative 47th newtons, which is a really small amount of force, and because they have really small masses. And then your answer to 13C should be 10 to the 12th, okay? So you would have to have a single proton with a mass of like the equivalent of kind of like an aircraft carrier to hold that electron in orbit around it if it was just a strictly gravitational field without the electromagnetic force. Okay, so does anybody have, on the sheet that I handed out, is there any of those else that you want me to go over? Type it in the text box. Is everybody cool with the problems that I gave you? If there's anything at all you want me to go over, let me know. We're good? Fantastic? Okay. Now, on the book problems, there's some of those specifically that I want to work. Okay? So, let me see. So, well, let me give a quick historical perspective. When you look at what Newton did, so one of the things that, as legend has it, Newton had published his works, the Principia, inertia, F equals ma, equal and opposite forces, all that good stuff. And so as the story goes, he was sitting around talking with some compatriots, and they said, wow, how do you reconcile your equations with Kepler's laws? So Kepler did his work early 1600s. Newton did his work later 1600s. And so, the guys kind of bemoaning the fact that the scientific community can't reconcile gravity with Kepler's works. So as the story goes, Newton comes along and he says, oh, I've got this figured out. It's not a big deal. And he pulls out this paper and he lays out this whole way of reconciling his gravitational fields with Kepler's laws. And the guy basically says, how long have you been sitting on this? And Newton goes, oh, I've had it worked out for a couple of years. And the guy said, why didn't you have it published? And Newton goes, it's not that big a deal. It's just some simple math. So what we're going to do is kind of work through this so you can kind of see how you can reconcile these two ideas together. Okay? So, let's say you want to look at problem number 42. Okay, so let's look at problem number 42. So, on 42, here's what you've got. So, you got satellite A, right? Here's satellite A, and it's going to orbit with the speed of 10,000 meters per second, okay? And satellite B is twice as massive as satellite A and orbits at twice the distance, okay? So we're going to let this be some distance, and then, so this is A, and then that's going to be B. And what is the speed of satellite B, assuming that both orbits are circular, okay? So here's the basic idea. So on 42, so you've got that it's orbiting at 10,000 meters per second. So if you look at what's going to happen, no, that's not. Hold on. Oh, I was looking at 43. My bad. Then I forget everything that I just said. That's actually 43. I misread it. We need to talk about 42. My bad. We're going to reconcile this right quick. I'm going, why doesn't this make any sense? I was looking at the wrong problem. So on 42, here's the star, and you got planet X orbits here with a period of 1 year, okay? And notice I just said 1 year, okay? And then planet Y orbits at a distance of 4 times that, okay? So you're out here, so this is planet X, and this is going to be planet Y, okay? And you want to know how long is an orbital period out there. So here's the deal. So if you look at this ratio of period Y to period X, okay? So if you look at a period being the square root of 4 pi squared, radius of Y cubed over big G, mass of omega, and then this is going to be the square root of 4 pi squared, radius of x cubed, okay? And then that's going to be big G mass of omega. So here's the deal. So all I did was I took that one big equation and I solved it for the two periods. So all we're going to do is we're going to look at this as like a ratio. Now, here's where the magic happens. So this is how you calculate the two periods, right? So look what happens. First off, I'm going to kind of reverse this and I'm going to square both sides. So I'm going to have the period of y squared over the period of x squared is going to equal 4 pi squared ry cubed over big G omega. And then this is going to be 4 pi squared rx cubed over big G omega. Now, look what happens. The 4 pi squared is going to cancel out. The big G is going to cancel out. The mass of omega is going to cancel out. And all you're left with is ry cubed over rx cubed. So at this point, Newton kind of gets this smirky little look on his face and goes, look, all this is Kepler's third law. Okay? But here's where this is important. Kepler's third law only works when you're comparing two planets that are orbiting the same center. Because what has to happen is that you have to be able to drop out the mass of the star, which in this case is going to be omega. If you were talking about like the Galilean moons of Jupiter, this would have to be the same mass of Jupiter. So this is why you can't use this like comparing a period of our moon to a period of a Galilean moon that's orbiting Jupiter, because you can't drop out and cancel out the masses. So Newton basically says, look, here's how you end up with Kepler's third law. You just start with this idea that the period is 4 pi squared r cubed over big G, the mass of the planet. You set it up as a ratio. Everything cancels out. Voila, you get Kepler's third law. So you can derive Kepler's third law from the Newtonian side of it, but you can't reverse it. You can't derive these from Kepler's third law, but you can take Newton's laws and end up with Kepler's third law. So if all goes well, then on 42, you should have, because it's got an orbital period of, I don't remember, 200 days. Yeah, 200 Earth days. And so if all goes well, you should end up with an answer of 1,600 days. Okay? So you have all these variables, and that should be your answer on 42. Now, let me talk about 57, because everybody has questions on 57. So in the name of time, I want to make sure I get through 57. Because I like 57, which is a cool hint that you'll probably see a question like 57 on the test tomorrow. So, here's the deal. So, you've got this conical pendulum, which looks something like this, okay? So, instead of just like a normal pendulum like this, okay, where you're just going back and forth in a plane, on this one, you're going around like this, okay? So, here's the whole key that you have to focus on, is that number one, it's moving in a circle. Okay, so you have to have some centripetal force acting, and you have gravity acting, and you have the tension in the string. So as this thing is going around, okay, if you were to isolate what was happening with this rubber stopper, you're going to have, and I got to remember what these numbers are. So here's this tether ball. You have a radius of 0.2 meters. And it is, hold on, 500 grams. So that means 0.5. So this is 4.9 newtons. Okay? And then it's a 1 meter long string. So that's 1 meter. And it's got a radius of 20 centimeters. And you want to find the tension in the string. So, here's the deal, okay? Here's the deal. What you're looking for is this side of the triangle, right? That's what you're looking for. So when you do that, here's the trick. If you know this is 0.2 meters, and you know this thing has a length of 1 meter, what you can do is you can find like an angle in here. Okay, because you know this is 0.2, you know this is 1, you can find an angle. So here's the other thing. Gravity is pulling down with 4.9 newtons. So that means, because it's moving around in a circle, that means this upward force over here also has to be 4.9 newtons, because it's balancing out that downward force. So here's the deal. So you know this side of the triangle is 4.9 newtons. So if you do your trig, you can find like this angle, which would be the same as this angle. If you want to make this 1 meter and then make this 0.2 meters out here, if that's easier for you to see, I don't care. But the whole thing being is that you're searching for this. Now, think this through. This is 4.9 newtons. You know this tension has to be bigger than 4.9 newtons because it's the hypotenuse of the triangle. Okay? So when you find this, your answer has to be bigger than 4.9. So if you do this right, okay, and that angle, depending upon which angle that you want to use, it's either going to be 78.5 or 11.5. So it's either 78.5 up here or it's 11.5 down here. This is a personal preference thing. You just have to figure out how you want to set up that triangle. So your answer to 57A should be 5 newtons. Okay? So what you're searching for is you're going to find that hypotenuse. Personally, I worked off the cosine of the angle. You can work off sine. It's whatever you want to do. When I worked off the cosine of that angle. Now, when you get to 57B, and this is where the back of the book gives you some weird answer. So on 57B, it says, what is the ball's speed? Okay? So you're trying to figure out how fast this thing is moving, okay, right, as it goes around in the circle. This is pretty complicated because the only way you can figure that out is if you know the value of the centripetal force. So let me draw this a little bit cleaner, okay? So you know this side is 4.9 newtons. You know that's 11.5 degrees. And if you can find this side of the triangle, that's going to be your centripetal force, okay? So what you're searching for is going to be this side. That's going to be that inward force that's making this ball travel in a circle, okay? So on 50